All right, so in the second half of 2.3, we are still calculating limits using limit laws. And this is just kind of looking at some special cases, specifically dealing with more piecewise defined functions like absolute value and greatest integer functions, so a step function. And then there's also some theorems that go along with this section as well, one being the squeeze theorem that we will talk about and you'll be working with. So as it says at the top, some limits are best calculated by first finding the left and the right hand limits, and these would be functions that are piecewise defined functions, because usually at some values you have one expression if you're approaching a number from the left side and then a different expression if you're approaching from the right. So we'll look at that in our examples. And as a reminder for you, that a limit as x approaches a of f of x exists and equals L. This is if and only if the limit as x approaches a from the left equals L and the limit as x approaches a from the right equals L. So the two one-sided limits have to equal or approach that same value in order for the limit to exist and for the limit to approach that value. So the first example says to show that the limit as x approaches 0 of the absolute value of x is equal to 0. So it's already giving us the answer. We just need to show it more as a proof. So the first thing I want to do, just as a reminder for you, is write out the absolute value of x as a piecewise function. So remembering that the absolute value of x is equal to x itself if the x values are greater than or equal to 0, and then it's equal to negative x, so the opposite of itself, if x is less than 0. So this is what I was explaining before. This is why it's best to evaluate the two one-sided limits. Here we have values of x that are greater than 0, so these values would be approaching 0 from the right side, and then here we have values of x less than 0, approaching 0 from the left side. So with the two different domains, we have the two different expressions. We have to make sure they're approaching that same value. So I need to find the two one-sided limits, the limit as x approaches 0 from the left of the absolute value of x, and also the limit as x approaches 0 from the right of the absolute value of x. So again, if we are approaching 0 from the left, we are approaching from values of x that are less than 0. So that would be using the expression negative x. So I can rewrite this and say this limit is really equal to the limit as x approaches 0 from the left of, and instead of writing the absolute value of x, I'm going to write negative x, because that's the expression to use for those x values. And now that I no longer have the absolute value bars, I can use direct substitution and just substitute 0 in for x, and I end up getting negative 0, or the opposite of 0, which is just 0. So the limit from the left is equal to 0. And then I can find the limit from the right. And from the right side, I'm approaching with values of x that are greater than 0. So in my piecewise function, those values correspond to the expression positive x. So then I can rewrite this limit as the limit as x approaches 0 from the right of just x without the absolute value bars, so using that expression from the piecewise function. And now that the absolute value bars are gone, again, I can just directly substitute 0 in for x, and I just end up getting 0. So because these two one-sided limits are equal or are approaching the same value, I can therefore say that the limit as x approaches 0 of the absolute value of x is equal to 0. Example 2 is still using that same piecewise defined function for the absolute value of x, but now we have a different expression as a whole. We have the limit as x approaches 0 of the absolute value of x divided by x, and we are showing proving that this doesn't exist. So again, because our limit involves absolute value, and absolute value is a piecewise function, we have to find the two one-sided limits. So I'm going to need to find the limit as x approaches 0 from the left of the absolute value of x over x, and also the limit as x approaches 0 from the right of the absolute value of x over x. So again, from the left, this is using values of x that are less than 0, which again, my expression then for the absolute value of x is negative x. So I can rewrite this expression as the limit as x approaches 0 from the left of negative x over x. And I don't just want to substitute in 0 right away, because then I'm going to have negative 0 over 0. That's not helpful. That's indeterminate. However, I can simplify this expression now since my absolute value symbols are gone. And x over x just simplifies to 1. So this whole expression just simplifies to negative 1, which then the limit of negative 1 is just negative 1. So actually, let me cross this out. I should have written it this way: the limit as x approaches 0 from the left of the expression simplifies to negative 1. And then using limit laws, it doesn't matter what x is approaching here. The limit of a constant is just itself. So this limit is negative 1. So then if we find the limit as x approaches 0 from the right would be from values of x that are greater than 0. Which then means I can replace the expression absolute value of x with the expression for values of x that are greater than 0, which is just x. So I have the limit as x approaches 0 from the right of replacing absolute value of x with just x over x. And again, I don't just want to directly substitute 0. That's indeterminate, 0 over 0, but I can simplify this to just 1. So then I have the limit as x approaches 0 from the right of 1. The limit of a constant is itself, so this is equal to 1. Now, these two values, the left and the right-sided limits, are not equal to each other. And since they're not equal, that means the limit as x approaches 0 from each side doesn't exist. So therefore, I have proven that the limit as x approaches 0 of the absolute value of x over x does not exist, since I showed that the limit from each side, the left and the right, do not equal the same value. All right, I'm just going to try to focus my camera a little better. There, hopefully that's a little better. I apologize. And then the next example is using or focusing around the greatest integer function. So just as a review, the greatest integer function is defined using this notation here, those double brackets. And those double brackets mean that you are then finding the largest integer that is less than or equal to whatever value is inside x. So just some examples. So if I had 4 inside of those double brackets, I would be finding the largest integer that's less than or equal to 4. And since 4 is an integer, this is just equal to itself. But if I, say, had 4.8 inside of the double brackets, now the largest integer that's less than or equal to 4.8 is also 4. So two ways to think of this, just as a reminder, is, well, one way would be to think of what integers this value is in between. It's in between 4 and 5, and so the largest integer that's less than the number would be 4 in this case. Another way to think of it is you're always rounding this number down. No matter what your decimal is, it's rounded down to the nearest integer. So then I'll just do another one more. So if I had negative 1/2, so rounding that down, or the largest integer that's less than negative 1/2 would be negative 1, because it's in between negative 1 and 0. Negative 1 is the smaller. So I'm not expecting, we work with the greatest integer function from time to time, but it's not a huge focus in calculus. We work with it, it's just not a huge focus. So I'm not reviewing with you how to graph it, how to graph different transformations of it, but I did include a graph so you can remember this is a step function. Now these never copy the greatest, so all of these line segments, the leftmost point on each line segment is supposed to be a filled in dot, and then the rightmost end point of each line segment is supposed to be an open circle. So you can kind of see from the graph what this means is if I were to, if I just look at this, well, I'll look at this one here since it's a little bit easier to see. So when x is 1, if I were to substitute 1 into that greatest integer function in those double brackets, it's an integer, it's going to equal itself. If I substitute in, say, 1.25, that's still going to round down to 1, so that y value is still 1. 1.5, that y value would still round down to 1. All the way up until 2, when now the y value would jump to 2. So that's why there's a short line segment over to when x is 2. It has an open circle since when x is 2, it doesn't equal 1 anymore. It now jumps up to a different y value. So I know I'm not here today, but I can explain that more to you if you have questions about the greatest integer function. However, what the focus is here is showing that the limit as x approaches 3 of the greatest integer function, showing that that doesn't exist. So we can look at the graph and see that it doesn't exist. So looking at, if we kind of focus on that x value 3, you can see if you approach 3 from the left side, you're approaching the y value 2, and if you approach 3 from the right side, you're approaching the y value 3. So you can see graphically why it doesn't exist. So a way to show that would be, and that's why we need to find the right and the left-sided limits too, is because it is piecewise. So if I were to show this, I would say the limit as x approaches 3 from the left of the greatest integer function. Well, I'll need to find that. I'm just going to write the second limit down as well. I'm also going to need to find as x approaches 3 from the right of the greatest integer function. But if I'm approaching 3 from the left, then this means I'm focusing on x values that are close to 3, but less than 3. Now, I say close to 3 because you can even see on the graph that there's a lot of values that are less than 3, and depending on where you are, you could be at a different y value. So close to 3 would be, for example, like this, or this line segment here, the one that's closest. So limits have that idea of closeness. And then if I'm approaching 3 from the right, I'm approaching for values that are greater than 3, but still close to 3. So if I'm approaching from x values less than 3, but still close to 3, so that would be, for example, say x is 2, and then 2.5, and then 2.75, and 2.9, and getting closer to 3 that way, all of those values are going to round down to the integer 2. So this would end up being the limit as x approaches 3 from the left of 2, which is just 2. And then if I'm approaching from the right, but again, so close to 3, so that could be, when x is 3.5, 3.25, 3.1, 3.01, so getting closer to 3 from that side, but still close to 3. Those values are all on that line segment where the y value is 3. So this ends up being the limit as x approaches 3 from the right of 3, which is just 3. And then again, like we had said for the example above, since these are not equal, this limit as x just approaches 3 doesn't exist. So I can therefore say the limit as x approaches 3 of the greatest integer function does not exist. Okay, so a way to see that graphically and then a way to see that written out. And one other thing just to add with this, the reason I wrote this here, so this 2 here would be the actual line segment y equals 2. This 3 here would be the actual line segment y equals 3. Just to clear that up if there were questions. I have one last example for you. Before we get to that, I have to introduce the squeeze theorem. And then before we get to the squeeze theorem, there's one fact that you need to know first. So we have, and this is kind of just using reasoning, it should make sense that if we have two functions f and g, if f of x is less than or equal to g of x, so that means the y values for f are all less than or equal to the y values of g, when x is near a, except possibly at a, then, and the limits of f and g both exist as x approaches a, then we can say the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. So again, if f is a function that's less than or equal to g, its limit as x approaches a should be less than or equal to the limit as x approaches a of g. So hopefully, reasoning-wise, that makes sense. So what the squeeze theorem says then, and this is another way to find limits when limit laws perhaps don't work. So if we have three functions, f, g, and h, and f of x is less than or equal to g of x is less than or equal to h of x. So g of x is kind of squeezed in between f and h. Again, when x is near a, except possibly at a, and the limits of f and h as x approaches a both equal the same number L, then, because g of x is squeezed in between those functions, since they have the same limit, the limit as x approaches a of g of x must also have that same limit of L. So this is a visual representation of that, where you have the function g, again near a, is squeezed in between f and h, and if f and h are approaching that same y value, then g must also approach that same y value if it's in between those two functions. And I mean, I could read the statement here. I know you can read it. It basically says that same thing. So then in this example, it says show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. We're going to use the squeeze theorem to show this. So the reason why we're using the squeeze theorem is because limit laws actually do not work here. I'll briefly explain why. I could rewrite this using limit laws because I have the limit of a product, so that's going to equal the product of the limits. So this would be the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. And here, we can just substitute 0 into x squared and get 0. But here, we cannot just substitute 0 in for x because this would not be defined if we substituted 0 in. So therefore, limit laws we can't use for this one. So in a case where limit laws don't work, and then the methods that we used in the examples on the front side also don't work. This isn't piecewise, so approaching from the left and from the right isn't going to change the fact the limit laws aren't working. We need something else to use, and in this case, the squeeze theorem is going to work. Squeeze theorem works not in every case, but in cases where you have sine or cosine, squeeze theorem will often work, and you will kind of see why as I explain this. First of all, I'm going to focus just on the sine of 1 over x. And I know that the range of sine, I'm focusing on the range because a limit is always equal to the y values, which are part of the range. So I know that sine of something, the range is between -1 and +1 for the sine function. So I can say that sine of 1 over x is in between negative and +1. So what I'm trying to start out by doing is set this up as having a function that's squeezed in between two other functions. That's where I'm headed to. So now this isn't the function I'm trying to find the limit of. I'm trying to find the limit of x squared times 1 over sine, or sine of 1 over x. So then I can just multiply everything by x squared. So then I would get negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. And now I do have the setup for using the squeeze theorem. This is my f of x here. This would be my g of x. Again, this is in the formula. And this would be my h of x. So the function I want the limit of is squeezed in between two other functions, negative x squared, positive x squared. I then will find the limit of the two outer functions as x approaches 0. And if those limits are the same, then I've found the limit of my function, because if these limits are the same by the squeeze theorem, my function must have the same limit if it's squeezed in between those functions. So I would be finding the limit as x approaches 0 of negative x squared, and the limit as x approaches 0 of positive x squared. Now here I can use direct substitution. If I substitute 0 in for x, I have negative 0 squared, that's just 0. And here, 0 squared is just 0. So these both have the same limit of 0. Therefore, the limit of my function must also be 0 when x is approaching 0. So to answer this, I'm going to say by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. Oops, kind of off the screen, sorry about that. And that, when you're using the squeeze theorem as well, that is the type of work you want to show. You want to show which functions are on the outside, find the limit of each to show that it's the same value, and then say by the squeeze theorem, that's our limit. So your practice is there, and the practice from the previous assignment, and then along with this one, I'll go over with you, or go over questions with you in class on Friday. One note I have with number 29, this is actually for number 30 as well. 29 though, the problem is having you find the limit as x approaches -4 of the absolute value of x plus 4. And there's one thing I want to explain with this, because it's not just the absolute value of x. So you might remember from algebra, or algebra 2, that if it's just the absolute value of x, the vertex is at 0, 0 when x is 0, and that's why these domains are when x is greater than or equal to and then less than 0. So because this is the absolute value of x plus 4, your domains aren't going to be with 0 when you set up your piecewise function. To find the vertex of an absolute value graph, you take the expression inside the absolute value bars and set it equal to 0 and solve for x. So in this case, x would be -4. -4 is the x value where the vertex is. So as a piecewise function, the absolute value of x plus 4 would be written this way. So this is going to equal itself, which is x plus 4, if the x values are greater than or equal to the x value on the vertex, which is -4. And then the other expression is going to be the opposite of itself, so the opposite of the quantity x plus 4, if the x values are less than -4. So in case a question came up with 29, usually questions come up that would be how to set it up. 30 also involves an expression that's different than this one. So that would allow you, or hopefully help you, set that one up as well. But we'll go through questions tomorrow.